Hi everyone. So this session is mainly a problem solving session on orders, but I'll quickly introduce orders for now. So suppose you have an integer n and an integer a which is co-prime to n, then order of a modulo n is the smallest positive integer d such that a to the power d is congruent to 1 mod n. Now, a few properties about orders are if a to the power x is congruent to 1 mod n for any x, then order, let's say the order, also we do not order by this, like order of a modulo n is d. This is a way to denote orders. And let's say a to the power x is 1 mod n, then d divides n. Can someone tell a proof of this quickly?
Can I say?
No. I mean, okay. Why can't it be like, let's say, let's consider 2. 2 goes to 4, 8, and then it period backs to somewhere here. Like, okay, eventually 1 does have to come. Okay, fine. I see that that proof might work, but how will you write it? Even with periodicity. Like, I guess just stating periodicity is bit incomplete, I guess. Okay. Assume D does not divide N. Then let N be dt times dt plus M. So you have, oh, wait, I wrote the question wrong. I have to say D divides X.
You confuse me for good time.
Oh, yes, D divides X. Okay, prove this. Yeah, how do you prove this? Yeah, so yes, exactly. So you have a to the power dt plus m is congruent to a to the power dt into a to the power m, which is congruent to a to the power d to the power t into a to the power m, which is congruent to 1 into a to the power m, which is congruent to a to the power m mod n. Now, m is less than d. But this is a contradiction because d should be the least positive integer, which is 1 mod n, such that a to the power m is 1 mod n. So therefore, if a to the power x is 1 mod n, then the order must always divide x. A corollary of this is order of a modulo n always divides phi of n. Okay, so the next thing is an application of orders, which is like Fermat Christmas theorem. It says if p is a prime which divides a square plus b square, then one of the following three conditions must hold. P is either 2 or p divides gcd of a comma b, or P is 1 mod 4. Okay. So yeah, try to prove this. P is 1 mod 4. Yeah, it seems like pretty random at first that how does this one come? So for that you need to somehow involve orders. Anyone, any ideas? I'll wait for 2 more minutes.
Okay, can I say?
My laptop is hanging 1 second.
Sure.
Yeah, I think it works now. Yeah. Anurag, were you saying something?
It was said, not me.
Okay, yeah, go on to that.
Yeah. So if we assume the first two are not true, let's say P is not 2 and P does not divide the GCD.
Yeah, like these two cases are just obvious, so just ignore these two.
Yeah. So if P divides and does not divide B, for example,
So like if P does not divide B, yeah.
then we consider that AB inverse the whole
Or then
square.
P cannot also divide A, because if P does not divide B and it divides A, then it never divides A square plus B square. So P does
Yeah.
not divide A comma B both.
Yeah.
Yeah, then.
And so then we can say that AB inverse the whole square is -1.
Yeah. So essentially I got A square plus B square is 0 mod P, which means that A square is minus B square mod P. Now you divide by B inverse squared on both sides so that you get A by B squared is minus 1 mod P. Okay, then.
Yeah, and so then we get that A by B the whole to the 4 is 1.
Okay, let's just say this to be some x, then x to the power 4 is 1 mod P.
And we just consider what is the order of X. The order of X with respect to P has to be 4 because it cannot divide 2 and it divides 4.
Okay, yeah. So now order of x modulo P should be should divide 4, which means it can be either 1, 2, or 4. But if it's 1 or 2, then x this thing should also be 1 mod P. but this is not the case. So it's 4, which means 4 divides 5 of p, right?
Yep.
So this implies 4 divides p minus 1, which means p is 1.4. So is this clear?
Yeah.
Okay, is it clear to everyone else also? Yes, no, anything? Okay, I'll assume that's a yes. So let's move on to some problems. Problem 1. Suppose n is a positive integer such that for all a comma b belonging to positive integers, n never divides 2 to the power a into 3 to the power b plus 1. Then prove that for any positive c comma d, n does not divide 2 to the power c plus 3 to the power d. It has, in some sense, the same idea as Fermat Christmas theorem. Not exactly, but like in some way. Any ideas, anyone? Yes, Anurag. I think this problem was also given as a joke by Atul in some meet or something. Okay, should I give a hint or something, or people are trying? Yeah, someone. Also, it's fine if you like to unmute. Like, if you can unmute, it's suggested that you unmute. Like, it's a better way. I think that complicates it a bit. Like, you can just do the problem directly. Like, you do not have to consider both of them individually. Because I guess doing that would be a bit harder. Let's see. Yeah, I don't directly see like how do you do that. What is D here? Or what is D? Oh, like you mean N, right? This is N. Yeah. Yeah. So let's assume for the sake of contradiction, there exists C comma D such that 2 to the power C is congruent to minus 3 to the power D modulo N. And you have that 2 to the power A into 3 to the power B is congruent to minus 1 mod N. It's never, right? So how do you get minus 1 from here on RHS? Like what do you do to go in like some this form? I mean, for some case, yes, that will be true. But how does this help us here? That's what I'm asking. Like the point is, let's take n to be say 5. It's possible to have c to be 2. Like there exists some d such that 5 divides 2 to the power 2 plus 3 to the power d. Like I'm not saying it's actually possible or not, but it is possible that this happens. And now c is 2, and like 2 to the power 2 is not 1 mod 5. What do you do then? Okay, so an idea here is, oh yes, that is actually a nice idea. Okay, yeah, I had a different solution. Let's just do that using this solution. So you have the 2 to the power c. Yeah. Okay, there's a better way to do this, like on this line only. So you have 2 to the power c congruent to minus 3 to the power d mod n. Obviously, 2 to the power c should be coprime to mod n. Like essentially n comma 2 and n comma 3 is 1. you can show that easily, because if not, like let's say 2 divides n, then if n is even, this thing is odd, so n can never divide this. Similarly goes for 3 also. So now 2 to the power c is co-prime to n, so there must exist some k, let's say order of 2 to the power c, like let k to be some p times order of 2 to the power c. Then 2 to the power k is congruent to minus 3 to the power dk mod n, or 2 to the power ck. This is one. One. Okay. Is one mod n. And now, oh wait. Okay, you do need k to be minus, k to be odd. What if k is even? Yeah, it's possible to have k as even, like if the order is just even. uh okay, but here's a better solution. So what do you do is, uh like it's on this, along this lines only. So let k to be the order of 2. Then you multiply both sides by 2 to the power. Uh, Also, you can without loss of generality assume c is less than k, right? So multiply by 2 to the power k minus c minus 2 to the power d into 2 to the power k minus c mod n. Now this thing is 2 to the power k, which means it's just 1. So this implies 3 to the power d into 2 to the power k minus c is minus 1 mod n. This implies n divides 2 to the power k minus c into 3 to the power d plus 1. And pick a to be k minus c and b to be d. There's a contradiction. Yeah, it's like almost on the same lines, but there when you raise to the power k, you cannot control k to be what do you say, odd. So is this clear, Zaman? Next. Okay, the next problem is uh, show that n divides phi of a to the power n minus 1, where a is greater than equals to 2 and n is greater than equals to 1 are integers. Yeah. Yeah. So what you have is like you consider a to the power clearly a to the power n is congruent to 1 mod a to the power n minus 1. Now if n is the order, then n should clearly divide phi of a to the power n minus 1. But it's possible that n is not the order. Like, how can you say that there exists no smaller x such that x to the power n 1 mod a to the power n minus 1? Like, it's possible to have a smaller x, right? What do you do in that case? Yeah, that works. So notice that if x is less than n, then a to the power x is less than equals to a to the power n minus 1. So it cannot be 1 mod n, 1 mod this thing. So we are done. Nice. Okay. Next question. Let me find one sec. Okay, let's just discuss what primitive roots are first. Primitive roots. Uh, so an integer g is said to be a primitive root modulo n if order of g is phi of n. So the point of this is there are phi of n co-prime numbers, like phi of n numbers are co-prime to n and less than n. So when you consider g to the power, like when you consider g to the power 1, g to the power 2, so on, modulo n, since the order is phi of n, it essentially covers everything. So g to the power 1, g to the power 2, g to the power 3, so on, then g to the power phi of n, then g to the power 1 again. This thing here covers all the co-prime residues model. For example, 2 is a primitive root mod 11. Like phi of 11 is 10. So let's check. 2, 4, 8, 5, 10. Then you get 9, 7, 3, 6, 1, 2. And notice that 2 to the power 5, like 2 to the power phi of 11 by 2 is minus 1 mod 11, like the halfway point. So is it clear what the primitive roots are? Zaman? Okay. So let me find the problem one sec. Okay, try this. Okay, before that I'll state a theorem. I do not know the proof of this theorem because like it's said to be like high tech or something, but it is a well-known theorem and like you should know this. If n greater than 2 is an integer, then n has a primitive root if and only if n is of one of the following forms: n is 2, n is 4, n is p to the power k, where p is greater than 2 and a prime. or n is 2p to the power k. So this is the theorem. So now try this problem. If p is a prime, then find number of primitive roots mod p. That is not correct. So like if there are p minus 1 roots modulo p, then that means that 1, 2, 3, so until p minus 1, everything must be a primitive root, but 1 is not a primitive root. The order of 1 is 1, right? No. For example, let's take 11. 11 has 4 primitive roots. Uh, like this was the cycle of 11. The primitive roots mod 11 are 2, 8, 7, and 6. I think so. Yeah. No. That is not the correct answer for sure. Let me find an example. 13 also has 4 primitive roots. Yeah. Try to think in a better way. Like, yeah, stop guessing. Like, try. Okay, this is the primitive roots mod 11. Try to see what's special about them. Like, from this cycle, maybe. Yeah. Yes. Yes, that is correct. Okay. So what you do is, you know that there is at least one primitive root modulo p by this theorem. So let's say it's g. Then you have, let's consider p as 7, g to the power 1, g to the power 2, g to the power 3, g power 4, g power 5, g power 6, and then you have 1 again. So now, when you consider like the orbit of g to the power 2, it's like g to the power 2, then goes to 4, then goes to 6. Right? For 3, it's g to the power 3, then goes to 5, then goes to, sorry, it directly goes to 6. Like 3 and then 6. 4 goes to first 2 and then 6. Okay, so like essentially, how do I say this? Whenever g to the power n you have, if n and p minus 1 are co-prime, then order is exactly p minus 1. Else, you can reach this thing in a smaller number of steps. Like this should be intuitively clear, I guess. So you just have to count for the cases whenever n is co-prime to p minus 1, which is 5 of p minus 1 cases. So like you can take a general, on this idea only, you can say that if n has non-zero primitive roots, number of primitive roots, then there are exactly 5 of n primitive roots. This is not that important result, but like a result worth remembering, I guess. Okay. So next is this problem. Let me check. For how many integers n with 0 less than n less than equals to 2017 into 2016 do we have n to the power n congruent to 1 2017? Take like 5-7 minutes and think about this, and then I'll present the ideas. Like you can say your ideas in the chat also. That's what I mean. Like think about this for a while. I'll be back in like 1 minute. Any ideas? Why is that true? Pi of n divides in. Yeah, that's fine. No worries. Oh, not really. Like, so what you are thinking is, if phi of n divides n, then sure. Sorry. Like phi of 2017, which is basically 2016, or 2017 is a prime. If 2016 divides n, then sure. This is n to the power n is 1 mod. That works. But that is not the only n which works. Like, it's possible to have order. Like, let's say there exists some n which has order n less than 2016. It's possible, right? Like, order should divide this thing. So it's possible to have order even as 2. So does it make sense what I'm trying to say? Yeah. So like, a general idea you should have is like, this is a commonly used idea in like some anti problems. That is too messy. Messy, not messy. Okay, bad joke. The World Cup is in like 45 minutes, I guess. You can do it in generalized way. Okay, so like one thing to consider is like, why do you have 2017 times 2016? That is a valid thing to think of, right? Notice that when you vary the base, like this n thing is in a cycle of modulo 2017. Like, if you consider n plus 2017, that is same as n mod 2017. But if you consider the power, that varies as mod 2016. Like, if you have some a, then a to the power x is congruent to a to the power x plus 2016 in the worst case. So essentially the point is n to the power n varies as modulo GCD of 2017 comma 2016, which is 2017 times 2016. So that is why you have a 2017 times 2016 in the question. So the point of this is, let's consider some n congruent to x mod 2017. Then you have basically x to the power x mod 2017, like the numbers mod 2017 I'm writing, x to the power x plus 2017, like the base is just the same, right? X to the power x plus 2 times 2017 and so on. This thing is x to the power x only. This thing is x to the power x plus 1, like you can take minus 2016. This thing is x to the power x plus 2, and you continue this, we'll essentially have x to the power x plus 2016. Not one of them. Okay, 1 second. So now you have this set. Notice that the set x to the power x, x to the power x plus 1, x to the power x plus 2, so until x to the power x plus 2016 is the same as the set x to the power 1, x to the power 2, x to the power 3, so until x to the power. One second. Oh, yeah. This should be by till 2015, because like you go up till 2016 times 2017, right? So if you have 2016, then x plus 2016 into 2017 will be greater than this. So this should be 2015. So we'll essentially have 2015, and this set is equivalent to x to the power 1, x to the power 2, so on to x to the power 2016 here. Like 2016 exponents, and then there's also till 1 to 2016. Like, is this clear why this is true? Mod 2017. Does it make sense? Or do I need to elaborate? I can maybe do it in a better if you want. Or is this clear? Zaman and Anurag. Like, if it's not clear, you can ask me which step is not clear. I can tell you that. Hello. Okay, I assume it's clear. So now you have like, not one of them will be one. Like, consider order of x. The first time you get a 1 in this set is at x to the power order of x. So like x to the power 1, x to the power 2, then you get x to the power order of x, which is 1. Then you get x to the power 2 times order of x, which is again 1. Until 2016, which is definitely 1 by Fermat's theorem. So essentially you'll have 2016 divided by order of x times 1 in this thing for x mod 2017, right? And now x can go from 1 to 2016. If it's 0 mod 2017, then x to the power x is never 1 mod 2017. So you just have to sum x goes from 1 to 2016. 2016 divided by order of x comma order of x. So is this clear? That how do we get this? Please say yes or no, anything. Nice. Now, how do you calculate this thing? Like, you cannot just manually calculate orders. It's hard to calculate that. Like, also one common mistake which people make is like someone which you were also making. You'll think that there is exactly one thing which is one, which is at like 2016. But you have to take into account that there can be more than one things. Like, do not confuse order with phi of n. They are different things. Okay. Yeah, try to think of that. How can we calculate this now?
Okay, so can I tell how to do this?
Sure, go on.
Okay, like you know that order 2017 of x will divide 5 of 2017. So
Yeah,
it's all devices of 5 of 2017.
it's
It's all devices of 5 of 2017.
uh, I mean we are taking x from 1 to 2016.
What?
X ranges from 1 to 2016.
Oh,
So
but
like,
like 27, they all will be divisions of 5 of 2017, right?
yeah, they will be divisor of 2016.
And where
But
does 2017 a prime?
no, yeah, 2017 is a prime.
So
But
like we can use the uh, what do you say? Primitive root, right?
Yeah, exactly. Yeah, so we use a primitive root. So like, let G be the primitive root. So you have G to the power 1, G to the power 2, G to the power 3, so on, G to the power 2016. Also, I thought Anurag, you were saying like these will just comprise of the what do you think?
Yes, yes.
Yeah, like this comprises of the order devices of 2016, but you do not know how often do they occur, right? That's what I was saying.
Okay.
Like you still have to check how often do they occur. Like 2 is a device of 2017, 2016, but how many numbers have order 2? You do not know that, right?
And we can bash cases now.
No, no. 20, will you batch 27 in cases?
No, no,
No.
like we have some kind of pattern, right? Like we have some kind of formula for number of primitive roots or a prime or something. If I know.
Number of primitive. Oh, no, no, not that way. Uh, sure. That we only have like number of primitive roots. That is 5 of 2016. But what about the other numbers which are not primitive root? So for that, there is like a general way. So like you have this cycle, right? Like G is a primitive root which exists, right?
Hmm. Yes.
So you consider a number G to the power n here. Like all the x from 1 to 2016 are covered in this cycle. So consider any G to the power n. What is order of G to the power n?
It's like 2016 by GCD of N and
Yes,
2016.
it is 2016 by GCD of n comma 2016. So essentially, this sum becomes x goes from 1 to 2016, 2016 divided by 2016 divided by GCD of x comma 2016, right? Okay, instead of x, we can take n. Like you'll have some G to the power n, right? Like for each x, there is a corresponding n such that x is G to the power n. And then n varies from 1 to 2016, right?
Yes, yes.
So
You
now
can
this
just
is
like
just sigma.
directly cancel 2016 and we will need to find the sum of GCDs.
Yes.
You can bash here.
This is like some multiplicative function nonsense. I don't remember.
Yeah, it is like, but you can bash the number. You can get like divisors of 2016 and then use how many divisors do they divide and just like that.
Sure. Like I'm not doing this. Like this is like not related to order. This is like normal NT. You can do this on your own.
Yes, yes,
Essentially,
yes.
the answer is there.
I
So is
agree.
this clear? Anurag, it's clear. He just said. Zaman. Nice. Okay, let me find another question. We have not done a question on the this Fermat thickness theorem, right? Yeah. Okay, so do this question. Prove that if x comma y are integers, such that y square equals to x cube minus 2017, then 3 divides y. I'll be back in like 2 minutes. Yeah. Okay, if we take modulo 9, then what is x cube mod 9? X can be 0 mod 9 also, right?
It's 0 and 1.
It can be -1 also.
Oh, okay.
What is 2017? 3, 10, 1. So this should be congruent to minus either like 8, 7, 8 or 9 mod 9. But there is no contradiction. Like y can be 0 mod 3, then it's 9 mod 9, and it can be 4 mod 9, then you get 7 mod 9 y square. Okay. Uh, sure. But that doesn't help you. Like, what does that give you? Like, x cube should be 0, 1 mod 9. But you still have a lot of cases to check. Like, okay, I'll just spoil this. No general modulo works. Like, you try to consider general mods, that does not help you. The thing is, you start somehow. No, modulo won't help. Okay, if you consider 2017 mod, then y square will have 1008 possible residues. Mod 2017. Not really helpful. The point is, you have to use this 2 power and 3 power somehow. So, like, you have a 2017 number. You try to make this look nice. So, what you do is you add 2025 to both sides. 2025 is 45 squared, and the other side becomes x cube plus 8, which is 2 cube. Now, this thing is of the form a square plus b square. We did something related to this in the starting of the class. Now, try to do this problem. What do you try now? Like, the obvious thing is like you assume 3 does not divide y for the sake of contradiction. What after that? Okay, then this means x cube plus 8 is not 0 mod 3, which means x cube is not 2 mod 3, 1 mod 3, which means x is 0 or 2 mod 3, right? Okay, the thing is, what you do is a square plus b square, why can't it be 0? Yeah, if x is 0 mod 3, then y square will be 2 mod 3, which is a contradiction. So x should be 2 mod 3. Yeah, so now the point is, this should remind you of Fermat Christmas theorem, a square plus b square. So what does it say? If p is a prime which divides y square plus 45 square, p should be 2, p should divide, like one of these should hold. This, p divides gcd of y comma 45, or p is 1 mod 4. So let's consider the case when p is 2. What happens in that case? Is it possible that 2 divides y square plus 45 square? Yes. So if 2 divides this, then 8 should also divide this, because 2 divides this thing. This means x should be even, which means this has v2 of at least 3. So 8 should divide y square plus 45 square. But you can check y square plus 45 square is never 0 mod 4. So that is not possible. So p cannot be 2. Now if p divides gcd of y comma 45, it means p can either be 3 or 5. If it's 5, that's the case of 1 mod 4 only. So it does not really give you much information. And p cannot be 3 because p does not divide y. According to the, for the sake of contradiction, we assume that. So it means all the primes dividing y square plus 45 square should be 1 mod 3, 1 mod 4, right? If we show that it is not true, then we'll be done. So now consider x cube plus 2 cube. You can factorize this to write x plus 2 into x square minus what? 2x plus 4, right? What was x mod? Oh. And also notice that x is odd. So let's say x is 2k plus 1. Then this thing is basically 2k plus 3 into 4k square plus 4k plus 1 minus 4k minus 2 plus 4, which is 4k square plus 3. Right. Now notice that 4k square plus 3 divides y square plus 45 square. This is 3 mod 4. If all the primes dividing this thing are 1 mod 4, then this should be 1 mod 4 only. Like if pi is 1 mod 4, then product of pi's should also be 1 mod 4, which means there should exist a prime which is 3 mod 4 and divides this thing. That means there's a 3 mod 4 prime which divides y square plus 45 square, which is a contradiction. So is this clear? This means that 3 should divide y. Any doubt? Is it clear? Yes or no, Anurag and Zaman? Okay, nice. Anurag? Okay, I assume it's clear. Yeah. Okay, another similar problem which you can try later. I'll just now end the class because of the World Cup. Is prove that n to the power 7 plus 7 is never a perfect square. This is you can check it on EOPS if you want solution. USA TSC 2008 P4. Okay, so that's it for the class. If you have any doubts, I'll stay for like 4-5 minutes, but I'll stop recording.